These kind of questions are very, very tricky. It seems like if you read the question, they are very obvious, but when you dive deeper into the statistics, you'll see sometimes they are not as clear of an answer as you might think they are. A veterinarian knows that 1% of the dogs in this country are infected with a virus. There's a test for the virus that is 98% accurate. This means it returns a positive result 98% of the time if the dog is infected with the virus, and a negative result 98% of the time if the dog is not infected. A vet decides to treat the dog that tests positive for the virus. Do you think this is a good decision, and explain? So when you first read through this, you might think, well, this is an obvious decision. If it's 98% accurate, let's just treat everybody that comes up with a virus or comes up positive for the virus, and we'll just treat everybody the same way. Not everybody thinks that way, as we well know after looking at the first few years of real life. So what we need to do is we actually need to look at a two-way frequency table of this situation. So we're going to start by assuming we have a very large population of dogs. We're going to say we have 100,000 dogs. So here's the possibilities you can have in this situation. So this is going to be my totals column. We have a column that's going to represent test positive and test negative. And then we're going to have rows that's going to be has the virus and does not have the virus. So remember from our section on two-way frequency tables that the bottom row and column is the overall total. So we're going to have 100,000 dogs. According to the information that we have, we know that 1% of dogs are infected with this particular virus. So the total for 1% of 100,000 that does have the virus is going to be 1,000. We find that out by taking 1% times 100,000. That means 99,000 do not have the virus. Okay, so the test is 98% accurate. So what that means is that if the dog has the virus, it will test positive, and if the dog does not have the virus, it should test negative. So this section right here that I'm marking through is test positive but has the virus. So that's where the 98% accuracy is going to come into play. So what we're going to do is we're going to take 98% times the 1,000 that's in that category. So when you take 98% times 1,000, you get 980. But that means there will be 20, because 1,000 minus 980 is 20. There will be 1,000 or 20 that has a false negative. That means they actually have the virus, but they test negative. That's a false negative. Conversely, we have 99,000 that do not have the virus, and of that 99,000 that do not have the virus, 98% of them should test that they do not have the virus. So 99,000 times 0.98 is 97,020. But that means there will be 2% that do have a false positive. That means they do not have the virus, but they test positive. So 99,000 minus the 97,020 that test accurately is 1,980. So then looking at the rows, we add the rows together, or the columns together. This column is 2,960, and this column is 97,040. What we're looking at is the probability that if they test positive, and only the probability that they test positive, what's the probability they really have the virus? So actually what that means is we're looking solely at this column to answer the question. So the probability that the test is accurate, if they they test positive and have the virus is 980 over the total of that column, which is 2,960. And when you take 980 divided by 2,960, what you get is 33.1%. So that means that of the 2,960 dogs that test positive, only 980 of them actually have the virus. 1,980 do not have the virus. So we actually get a very large amount of dogs that give us a false positive. So it is not a good idea to test all the dogs to treat all the dogs for this virus, because there's a very strong chance that there's actually these positive tests give you a false positive and they actually do not have the virus. So there might be reasons why you wouldn't want to treat every dogs. Maybe there's some very serious side effects. But just because you get a positive test does not mean automatically start treating these dogs. You probably need to test them multiple times to hopefully guarantee that they do have the virus. Hopefully they don't have the virus, obviously, but to make sure that we are not getting false positives. Let's do one more that's similar to that. Factory produces and packages hamburger patties. It is known that 5% of the patties are not the correct weight. The scale at the factory is 99% accurate in identifying whether or not a patty is the correct weight. A manager at the factory decides to throw out any patty that is identified as not the correct weight. Do you think this is a good decision? And explain. This time instead of saying that it's test positive and test negative, let's say it's going to be weighs correctly and does not weigh correctly. So weighs correct and not correct. And then our rows are going to be that the patty is actually correct. And then patty not correct. Okay, we will also assume 100,000 patties. That is just a very safe number to assume. So our situation is that this scale is 99% accurate, and we know that 0.5% of the patties are not the correct weight. So if 0.5% of the patties are not the correct weight, then we would take the 100,000 patties in our sample and take that times 0.5%. So that's 0.005. That only gives us 500. So there are 500 patties that are not going to be the correct weight, or at least not actually the correct weight. That means there are 99,500 that will be the correct weight. That's 100,000 minus 500. So of those patties that are not the correct weight, if this scale is 99% accurate, we have patty not correct and it weighs not correct. So that's that cell right there. So if you take 500, let's try that again. Not erase so much this time. If you take 500 times the 99% accurate scale, you get 495. But of those 500, you will have 5 patties that are not correct. The patty's not correct, but it actually weighs correctly. If you got 99,500 patties that weigh correctly, then 99% of those 99,500 should also be the correct weight, and that is 98,505. But the leftover ones, when you take 99,500 minus 98,505, you have some patties that are actually the correct weight, but they did not weigh correctly. It says they weighed incorrectly as the wrong weight, but they really were the correct weight. So when we add our columns up, we get 98,510 and 1,490. So the question is, the manager decides just to throw out any patty that is not identified as the correct weight. So that is actually this column right here. This is the not weighs correctly column. The scale says it did not weigh correctly. So this is what we're looking at. So this area right here, this is your not weighs correctly, but the patty is actually correct. So what that means is there is a very strong probability, 995 over 1,490. And when you divide that out, you get approximately a 66.4% chance that they're throwing out good patties. 66.4% of the patties that weigh incorrectly are actually good patties, so it is not a good decision for the manager to do this. So as I said earlier, it is very difficult on some of these situations. What it seems like it's a very obvious thing to do when you really dive deeper into these two-way frequency tables, the decision is not as obvious as you might think.